everyone. So tonight we have two really big, exciting topics to talk about. We are going to introduce the second fundamental theorem. So we've talked about the first fundamental theorem of calculus, and now we're going to unwrap the second one. And then we're also going to talk about accumulation functions. Both of these are very highly asked questions on the AP exam, so we are definitely in for two good topics. All right, so let's get started. Okay, the second fundamental theorem of calculus is exactly what I've written down here. It's a method for taking the derivative of an integral. So we want to get that down, and then we're going to talk about the formulas and the process for how we do this. Okay, so I have a couple formulas here that we want to definitely get down. And the first one is more general. It says that if we want to take the derivative of an integral from c to x, and notice over here I'm telling you that c must be a constant, of f of t dt, the answer is simply f of x. All right, why does that make sense? Well, I want you to understand that, remember, derivative and integrals are like opposites, so they just cancel out. And then the big concept with the second fundamental theorem is that when c is a constant, whatever your upper bound is gets plugged in place of t. And so the answer is simply just a function in terms of x. Okay. More likely than not, though, our upper bound is not simply an x. It is a function of x. So if I look at the second one, which is the formula that I'd more have you memorize, it's again taking the derivative of an integral, again from a constant, this time to a function of x. We've talked about this before, like x squared or 3x or something like that, of f of t dt. Okay, so two things are happening. First, you get f of u. Again, the derivative and the integral cancel each other out. How do we evaluate this, though? First of all, it's f of u. So whatever the upper bound is, you plug it in for t, times the derivative of the upper bound. So two steps. Plug in the upper bound, in for t, then take the derivative of the upper bound. That's it. All right, we're going to practice a bunch of these. Let's get going. Okay, so once again, there are two basic steps that we need to follow every time we want to do one of these problems. First is to plug in upper bound. And second is to take the derivative of upper bound. Okay, so those are the two steps we're going to follow as we approach these. Again, these are problems when you're taking the derivative of an integral. And you'll notice that for these, you will have different variables. Okay, the variable at the upper bound here is 2x, and you're doing ddx, but then in the actual function, we have a t cubed and a dt. Okay, so that's how you're going to recognize these problems. All right, so let's go ahead and jump in. So the first one, the derivative from 0 to 2x of sine t cubed dt. Okay, so remember, the derivative and the integral cancel each other out. All I'm worrying about is doing these two steps. So I'm going to take sine, instead of t, I'm going to replace it with 2x quantity cubed, and then I'm going to do times the derivative of the upper bound, so times 2. Okay, I can do one more step to kind of clean this up. 2 sine 2x cubed would be 8x cubed. And that's it. All right, so let's go ahead and try the next one. All right, so if you notice, this one has our bounds a little bit different. Our lower bound is the x squared and our upper bound is the 3. We want to go ahead and change that right away. All right, so we're going to go ahead and first thing first, we're going to rewrite this as negative derivative of the integral from 3 to x squared, the cubed root of 8t plus, t to the 4th, and then dt. Okay, now we're ready to go ahead and take the derivative. So we're going to have, our answer is going to be negative. Remember, two steps. Plug in the upper bound. So it's the cubed root of 8x squared plus x squared to the 4th, all under the radical, and then times the derivative of that upper bound, 2x. All right, so I can do a little bit of cleaning up here. I can say negative the cubed root of 8x squared. I can even say negative 2x. Let's put that in front. Times the cubed root of 8x squared plus x to the 8th. And that's it. That would be my answer for this second problem. All right, I want you to go ahead and write the number 3 and 4 down. They're really straightforward, just like the two we just did. Try them on your own. Pause the video, try them on your own, and then come back and see if we have the same answers. Okay, so let's compare your answers with mine and see if you got them right. So in this very first one, we're going to go ahead and, again, that derivative will cancel out the integral. I'm going to plug in this upper bound in everywhere where I see a t. So I'd have x cubed sine x cubed squared times the derivative of the upper bound, so 3x squared. Clean that up by multiplying my x cubed and my 3x squared. So I got 3x to the 5th, squared my x cubed, and got x to the 6th. All right, the next one. This time I noticed that those bounds were backwards, so it's the derivative of the negative integral from 0 to 4x. Then I went ahead and, again, plugged in my upper bound in place of t, and then took the derivative of the upper bound. And cleaned that up, and I got negative 4 square root of 256 x to the 4th plus 2. All right, so now that I think we have a kind of good handle on that, we're ready to move on to accumulation functions. Okay, so accumulation functions are going to often be given with a graph, and you'll see that they will start off with information that says something like this. The graph of f is defined below, so this is the graph of f. Okay, I want to recognize that. Then it says, let g be defined as g of x equals the integral from 1 to x of f of t dt. All right, so what that tells us is that g is equal to the area under the curve, the integral, from 1 to x of f of t dt. So if I'm asked in this first problem to evaluate g of 3, now let's think about this. What is the 3 representing? What place is it holding? It's holding the x place. So I'm going to take this function, this g of x function that was given to me right here, and I'm going to replace the x with 3. So I'm going to say the integral from 1 to 3 of f of t dt. And that means I want the area under the curve from 1 to 3 of f of t dt. So we've done these before, and whether you want to go and find all the areas and then use it, or if you just want to find the one that we need, I'm going to go ahead, because I know that through the course of this problem I'm going to need lots of different areas. So I'm going to go ahead and pause the video, find all of the different areas, kind of break it up into different chunks. So we can do that together. I'm going to break this up into a triangle here, a rectangle there, a little triangle. We have a triangle here and a triangle here, and in the middle here you have a rectangle with a semicircle cut out. So I'm going to ask you to pause the video right now and find the area of all of those, and then come back and see if we agree. And then we'll go from there and answer these questions. Okay, so let's take a look at our areas and see if you agree. They're all pretty simple shapes, so hopefully we got the same answers. And now we're going to go ahead and answer a few questions. So the integral from 1 to 3 of f of t dt would be the area under the curve from 1 until 3. So notice I have to start at 1 and end at 3. So you can see that that's just a triangle with an area of 4. Okay, the second one is g of negative 4. And so again, let's plug in our negative 4 in place of x. So is the integral from 1 to x, so that's where our negative 4 is going to go, of f of t dt. Okay, so obviously I don't like the way this is written, so I'm going to rewrite it as negative, the integral of negative 4 to 1 of f of t dt. All right, so I'm going to go between negative 4 here and positive 1. So I can see that I had an area of 8 and 1. Those were both beneath the x-axis, so that would have been a negative 9. But because it's already negative, so it's negative of negative 9, so I would say my answer here is positive 9. Okay, we have two new questions for you here, g of 1 and g of 8. I'd like you to pause the video and go ahead and answer both of those, and then come back and see if we agree on our answers. Okay, so let's compare your answers. The first one should have been a nice and easy one for you. G of 1, again, I'm replacing the x value with 1. So the integral from 1 to 1 of f of t dt is simply going to be 0. Remember, if those bounds, upper and lower, match, then your integral is simply 0. Okay, g of 8. So again, I'm replacing my upper bound here with 8. So the integral from 1 to 8 of f of t dt. So I'm just adding from 1 to 8. So I added up all of those areas and got 22 minus 2 pi. Okay, so this is not anything new that we've done, that we haven't already done. This is just presenting it in a different way. All right, so we're going to continue on with more questions like you would be asked from this, with these kind of graphs and this kind of accumulation functions. Okay, as I look at the next two questions, it's asking us to evaluate g prime of 0 and g prime of 5. Okay, so this is where the second fundamental theorem is going to come into play here as we try and take the derivative, g prime, of this function. So it's asking us to take the derivative of an integral. So if they're saying to go ahead and take g prime of x, well, that's taking the derivative of this right here, and we just talked about that. I'm going to take the derivative of the integral, okay, and once again you can see that you have an upper bound of x, and we are talking about t's in our function. Okay, so what do? Well, we replace the upper bound, and then we take the derivative of the upper bound. So our answer here would be f of x, and then times the derivative of the upper bound would just be 1. So what this is telling me is that when I'm taking the derivative of g, like it's asking me in E and F here, all I'm doing is it's really asking me what is f of that value. And remember, this is the graph of f. And so if I'm asked for the g prime of 0, what it's really asking me for, okay, is, remember, g prime of x is equal to f of x, so it's really asking me for f of 0. And so f of 0 here is simply, I'm literally reading the point, what is the output when x is 0? Well, that would be right here at -2. So my answer for this first one is -2. Okay, so this is the crucial key fact that you have to get in your brain, that the derivative of g is f of x. And of course, if you ever get stuck, you can go back to the original, what is g of x equal to, and take its derivative. And remember, the derivative of an integral cancels out, upper bound gets plugged in for t, take the derivative of the upper bound. All right, so g prime of 5, same thing, it's just asking me for what's f of 5. And so what is f of 5? Again, go to the graph. My answer is +2. And so that's how I answer those two questions. Really simple if I remember the connection between taking the derivative of that integral. Okay, g and h here are asking us to take the second derivative of g. So that means we have to take the derivative and then take its derivative. All right, so let's again go back to the function that we're starting with right here. So if I start with g prime of x, which we just talked about, okay, again, that's taking the derivative of, so that's asking us to do d dx of the integral from 1 to x, of f of t dt, which is what the second fundamental theorem talked about. Plug in your upper bound, f of x, and then take the derivative of the upper bound, so times 1. All right, so if that's g prime, then what is the second derivative? Well, g double prime would have to be f prime of x. All I'm doing is taking the derivative of what I just got for my derivative. All right, and so I end up that the second derivative of g is really f prime of x. So this is really asking the question. Remember, this is the graph of f. So this is really asking the question, g double prime of 5 is really asking what is f prime of 5. All right, let's stop and take a think. Stop and think about this for a second. What is f prime? The concept there is f prime is slope. So the question here is, what is the slope of the graph at 5? So when x is 5, all right, right here, when x is 5, what is the slope of the graph? So at this point right here, what would I say the slope is? Well, I would definitely say that that is a horizontal tangent. That's a local min. And so I would say that the slope here is equal to 0. And so g double prime of 5, which is the same as the f prime of 5, is equal to 0. All right, I want you to pause the video and go ahead and do letter H and come up with an answer. Okay, so this again, the second one is asking us for the g second derivative at 1. we just went through how that's really asking us for f prime of 1, which is, of course, the slope of the f graph at x equals 1. So what I did was I went ahead and I looked at where x equals 1 on my graph here, and I said, what is the slope of this line? So I went ahead and darkened it a little bit in blue, so I knew exactly what I was looking at. And of course, slope is rise over run. So I was just counting rise of 2, run of 1. And therefore, I knew that my slope is a positive 2. All right, hopefully you're grasping this. If not, go back and start this slide, start this from the beginning. I want to make sure that you're understanding, because these are such common questions. Being able to identify and answer g of a number, g prime of a number, and g double prime of a number are extremely common questions on the AP. So I want to make sure you come into class next time with a firm understanding and ready to answer questions like this. All right, we're not done. We're going to go ahead and answer a few more very commonly asked questions of these accumulation functions. Okay, the next question here, again, very common on the AP, is to say, find all values of x in the open interval -8 to 8 in which g attains a relative minimum. Justify your answer. Okay, so we're talking here about a relative minimum. So I want just to think about just for a second, take the graph away and just think what I've taught you about relative minimums. If you are asked to find a relative minimum of g, what do? Well, we take the derivative of g. You find the critical values by setting that derivative equal to 0, and then you do a sign chart. Well, guess what? We're going to do the exact same thing here. We're just using our graph as our function. Okay, so remember, this is the graph of f. I can't stress that enough. They are telling you the graph of f is given below. Okay, g is defined as the integral of the graph of f. So, if they're asking us in which g has a relative minimum, we have to focus on when is g prime of x equal to 0. All right, so let's think about this. If I'm taking the derivative of g, all right, that would be the derivative of the integral from 1 to x, f of t dt. I know we've talked about this a lot, but I want to get this in your brain. That's the same as f of x. So they're saying, when is the function equal to 0? When is the graph that they gave you equal to 0? Well, that's simply asking, when does this graph cross through the x-axis? And you can see we have several different answers. We have the answer x equals, let's see here, -7, x equals 1, and x equals 8. Okay, now, what would we do at this point if we were asked to find this with a regular function? We would make a sign chart for those values. All right, so I'm going to go ahead and make myself a number line, and I'm going to put on here that this is g prime and g. All right, so g prime, remember, is the same as f. And so we're going to go ahead and mark on here -7, +1, and +8 as my zeros. Okay, now, to the left of -7 is g prime, which we just said g prime is f. That's what this told us right here, okay? Is that positive or negative? Well, the graph of f is above the x-axis, so I would say it's positive. Between -7 and 1, it's negative. Between 1 and 8, positive. Okay, so that allows me to say that g is increasing, and then it's decreasing, and then it is increasing. All right, then my relative min is very easy to see, that my relative min occurs at x equals 1, and the reason, to justify your answer, is because g prime changes from what? Negative to positive. And so that's where my relative min occurs. Okay, so again, we're drawing on a lot of knowledge from before. It's just we're looking at it in a very different way. We're using this graph and this accumulation function and the fact that g is defined as the integral of f. Okay, so we're tying all this together. So again, if you're not understanding, go back and rewatch it. It's so important that you get this and that you're able to do this in class tomorrow. All right, we're going to go ahead and try a couple more questions. Okay, our next question is asking us to find the absolute maximum value of g on the closed interval -8 to 8. Justify your answer. Okay, again, go back in your memory. What does it mean to find the absolute maximum? Well, again, I'm finding my critical values. I'm looking for when g prime of x is equal to 0, which we just reviewed and discussed. That's really asking us when is f of x equal to 0. And we just found those values to be x is -7, x is 1, and x is 8. And then when you're testing for an absolute maximum, you are not doing a number line test. Instead, we're doing a closed interval test. And we're doing that closed interval test with G. So here is going to be our X values, and here is going to be our G of X. All right, so this time I'm going to go ahead and put -8. Remember your closed interval, you use your interval that's given and all of your values that fall in between there. So I'd say -8, -7, 1, and 8 go on there. All right, so what does this mean? I'm evaluating then G of -8. Well, again, think back a couple questions ago. G of -8 is really asking us to plug in -8 in for X in this integral. So that means I'm really evaluating the integral from 1 to -8 of f of t dt. Again, this is the graph of f. Okay, so of course that's the same as negative, the integral from -8 to 1 f of t dt. All right, now I don't have all my areas on here. Hopefully you still have yours on yours. I'm going to just pause this for a second and get them back up on there. Okay, so now that I have all those areas back on here, it's going to be pretty easy to answer these questions. Okay, so I would say it's the negative of, let's see here, it's 1 and then minus 3 plus 8 is 11 plus 1 is 12. So I would say 3 minus 12, or I'm sorry, 1 minus 12, which is obviously negative 11. The negative of that is positive 11. Okay, so the value of G of -8 is positive 11. All right, now we're going to go on to the next one. G of -7. So again, that's the integral from 1 -7 of f of t dt. Okay, so I'm going to go ahead and evaluate that one. Okay, I want you to go ahead and pause the video, and you should quickly be able to come up with that one, and we'll go on from there. Okay, so this one should have been pretty easy to do because really I'm just looking at all of this from -7 to positive 1, and so that's the 3, 8, and 1. Add that together, that's 12. It's under the x-axis, so it's negative, but you're going to negate that, and so you get positive 12. All right, thankfully we have already evaluated G of 1 and G of 8 earlier in our notes, so we're going to go ahead and fill those in. We know that this one was 0, and G of 8 we found to be 22 minus 2 pi. Okay, so now I have to decide which of those is the largest. So clearly it's between 12 and 22 minus 2 pi. 2 pi is like 2 times 3, so it's about 6. 22 minus 6 is certainly larger than 12. So I would go ahead and say that the absolute maximum is in fact this value. So we're going to go ahead and write that up. And I'm going to do that up here just so that I have the room. So I'm going to go ahead and say the absolute maximum is at x equals 8, and it is a maximum of 22 minus 2 pi. Okay, so that finalizes this question. All right, and we're going to go ahead and move on to one last question with these accumulation functions. Okay, so this last question is asking us to find the x-coordinate of each point of inflection on the graph of G between -8 and 8. Justify your answer. Okay, so now we're talking about points of inflection. So everything from the beginning of the year is coming back to life here. Okay, so points of inflection are, of course, when, for G, would be when the second derivative is equal to 0 and there is a change of sign from positive to negative or negative to positive. And so again, let's review. All right, if we are taking the first derivative, G prime of x here, that would be f of x. So G double prime of x, which is what I'm looking for here, is f prime of x. So that would be the slope of this very graph right here. So what we're asking is, when is f prime of x? When is the slope of this graph right here equal to 0? All right, so we're looking for our horizontal tangents, and clearly I can see some here all the way between -4 and 0, and I can also see one here at 5, and that would be about it. Okay, and so I'm going to go ahead, and I also have an undefined kink here at -7. So I guess I could also say I had a kink at 3, and also at positive 7. So those are a lot of different places, all right? So, because we want to know when it's equal to 0 or when it's undefined. So I'm going to go ahead and make my number line and put all those different values on there. All right, and I'm going to call this G double prime and G. And so we started off, we had -7, and this time, I'm sorry, yep, -7. Really all the values between -4 and 0. So -4, we're just going to kind of zero this all out down to 0. And then at positive 3, we have an undefined. And at 5, we have a 0. And at 7, we have an undefined. -7 was also an undefined. All right, so now we're going to go ahead and fill in the values in between. So remember, we're talking about the slope. Okay, this is the slope of f. And so what would I say about the slope of f between -8 and 7? I would say it's decreasing, so it's negative. Again, between -7 and -4, negative. Then it zeroes out for a while. Then between 0 and 3, I would say positive. Between 3 and 5, it's downward, so it's negative. 5 and 7, it scoops back up, positive. And then from 7 to 8, it was negative again. So remember, second derivative talks about concavity. So this is concave down, concave down, concave up, concave down, concave up, and concave down. All right, so where are our points of inflection? Our points of inflection is when we change sign. All right, so we would say that we are changing sign here, right here at 3, and again at 5, and again at 7. Okay, we're not changing sign at -7, negative, and then between here there was just a whole flat line, so we're not changing sign in there. So we're going to go ahead and say that we change sign at x equals 3, 5, and 7. So those would be our points of inflection. So points of inflection at x equals 3, 5, and 7. And that's because G double prime changed sign. All right, so we now have gone through several different applications of these accumulation functions. I can't stress enough, almost every single AP has one or part of these as a short answer question. So we're going to get a lot more practice with this next time, and actually our next video is going to continue on with these and do some different types of application problems with these problems. So I hope you have a great night, and I look forward to seeing you in class tomorrow.